Next up, we have formal charge. Formal charge is the hypothetical charge on an atom in a molecule or polyatomic ion. So formal charges allow us to determine the correct Lewis structure when there's multiple valid Lewis structures possible for a molecule or polyatomic ion. I'll show you what I mean by that, but just know that if there's more than one way of drawing the Lewis structure, then we can use formal charges of the atoms to determine the correct or best Lewis structure. Here's how it works. You take the number of valence electrons that the atom has. So we got to do this for each atom in the molecule or polyatomic ion. Take the total number of valence electrons and subtract from that the number of electrons around that atom in the Lewis structure. Now let me clarify. So that second part here, is the sum of the bonds and lone electrons. Notice it doesn't say lone pairs, lone electrons on that atom in the Lewis structure. So look at your Lewis structure, see how many bonds and lone electrons it has, add those up, subtract that from the number of valence electrons that that atom has. So here's some guidelines, some things to think about when you're determining formal charges, trying to determine which of the multiple possible Lewis structures is the correct or best Lewis structure. So it says the most likely Lewis structure for a molecule or ion is the one in which the formal charges on each atom is 0 or as close to 0 as possible. So the lower the formal charges, the better on each of the atoms. Negative formal charges should be assigned to the more electronegative atoms. So let's say you have an option between two atoms where one's negative, one's positive. The more electronegative one is the one that should be the negative one. And then adjacent atoms should not have formal charges with the same sign. So if you have that, that's probably not the correct Lewis structure. Let's take a look on page 269. There's an example at the bottom of the page. So let me walk you through this one to determine the formal charge of each atom in that first Lewis structure on the left. Again, both are valid. Each atom satisfies the octet rule, and so we need to figure out which one is better. Is that double bond between nitrogen and chlorine or between nitrogen and oxygen? All right, let's start with chlorine on the left. 7 valence electrons minus, we have 4 lone electrons, 1, 2, 3, 4, 5, 6. So that gives us a formal charge for the chlorine of +1. Nitrogen has 5 valence electrons, 5 minus 1, 2 for the lone electrons, 3, 4, 5. So if you want to think about it, each atom gets one of the pairs in that bonding pair of electrons. So again, that's 5 minus 1, 2, 3, 4, 5. Nitrogen is 0. Oxygen, 6 valence electrons, minus 1, 2, 3, 4, 5, 6, 7. So it's got to be in that order. Valence electrons minus the sum of the electrons around that atom. So not too bad. Those are pretty close to 0. 1 on the right, so 7 for chlorine minus 1, 2, 3, 4, 5, 6 lone electrons, 1 bond, that's 7, that's 0. Nitrogen will be the same as the Lewis structure on the left. It has a double bond, 1 single bond, and a lone pair, so that's again 0. Oxygen, 6 valence electrons, minus 1, 2, 3, 4 for the lone electrons, 5, 6. So the formal charges in this Lewis structure on the right are closer to 0 than the other Lewis structure, so this is the correct Lewis structure. All right, let's try some more examples. So there are 2 ways of drawing the Lewis structure for carbon dioxide. In fact, every year when we're doing Lewis structures, I have a student ask, why is it 2 double bonds in carbon dioxide instead of 1 single and 1 triple? Well, let me explain. It has to do with experimental evidence. So I'm not even looking at formal charges now. Experimental evidence shows that the bond lengths in carbon dioxide are the same. So remember, bond order affects bond length. So if the bonds are the same length, can't be 1 single, 1 triple. Triple bonds are shorter than single bonds. So it must be 2 double bonds. Let's confirm this with formal charges. Go ahead and determine the formal charge of each atom in each of those Lewis structures. Pause the video and we'll compare. So it looks like the Lewis structure on the left is better than the one on the right. Let's try a couple more examples. There are two ways of drawing the Lewis structure for Cl2O. Here they are. Go ahead and determine the formal charge of each atom in each of those molecules, in each of those Lewis structures, I should say, and see which one is a better Lewis structure. Go ahead and pause the video. So it looks like the Lewis structure on the left is better, so we'll go with that one. Let's try one more example. Two ways of drawing the Lewis structure for nitrous oxide or dinitrogen monoxide. Again, same thing, pause the video. So it looks like the one on the right has formal charges closer to 0. Oxygen is more electronegative than nitrogen. And so oxygen should get the negative formal charge in this case. So that one looks good there. Next up is resonance. Now be careful. This one is different. So sometimes there are equivalent Lewis structures. So those last examples we just saw, they are not the same, not equivalent Lewis structures. But what if you have equivalent Lewis structures for a molecule? Here's when it happens. It says occurs when a double bond occurs in more than one possible location in a correctly drawn Lewis structure. Here's an example. We saw this just last lesson. There are 3 resonance structures for the resonance hybrid, it's called, of sulfur trioxide. So let's go ahead and draw those 3 equivalent Lewis structures. Go ahead and pause the video and draw all 3 just next to each other. So here are the 3 equivalent Lewis structures for sulfur trioxide. That double bond can go bottom left, it can go top, it can go bottom right. They're all exactly the same. So the question is, which of those Lewis structures is the correct one? The answer is sort of all of them, none of them. Probably none of them might be the best answer. Before we move on though, and I show you another way of drawing this and explaining what's going on here, is what is the bond order in this molecule? So we talked about bond orders. Bond orders apply to individual bonds. They also apply to molecules. So to determine the bond order in a molecule, take the number of bonds and divide it by the number of bonded atoms. Before we do this one, let's use a little bit easier one. Let's look at carbon tetrafluoride. What is the bond order in carbon tetrafluoride? Well, we have 4 bonds divided by 4 bonded atoms, and that gives us 1. So in this molecule, bond order is 1. How about sulfur trioxide? This time we have 4 bonds, 4 shared pairs of electrons. Even though we have a double bond is really 1 bond, we're going to think of it as 2 bonds here. It's 2 shared pairs of electrons. So 4 bonds divided by 3 bonded atoms, we get a bond order of 1.33. And well, that's significant in what I'm about to show you. So again, if one of those Lewis structures was correct, that would mean that there are 2 different bond lengths in that molecule because double bonds are shorter than single bonds. That's not the case. The bond lengths are the same. So how is that possible? It says experimental evidence shows that resonance structures don't actually exist. The multiple bond that is shown in more than one possible location is actually divided up between those locations due to something called delocalization. So the electrons that make up that pi bond, the second of the double bond, are delocalized, meaning they don't belong to just sulfur and one of the oxygens. They belong to sulfur and all of the oxygens. And those electrons that make up the pi bond are able to move around between sulfur and each oxygen. So let me show you another way of drawing the resonance structure for sulfur trioxide. So the oxygens have sigma bonds that they form with sulfur, those single bonds there. And then the other pair of electrons are delocalized and they can move around. Let me show you how to show that. So those delocalized electrons are often shown with a dotted line. So they're not permanently here or permanently there, permanently there. They're moving around within this molecule. So same for anything, any molecule that has a double bond, that can occur in more than one place in the molecule. All right, take a look on page 275. The example this time is sulfur dioxide. So once again, if you draw the Lewis structure, you'll see that there is one double bond and one single bond. And that double bond can move around to either side. So two possible resonance structures for sulfur dioxide. How about this? What is the bond order in sulfur dioxide? Go ahead and figure that out. So this time we have three bonds and two bonded atoms. So 3 divided by 2. So if you want to think about it, each of the bonded atoms has 1.5 bonds because those delocalize electrons. Oh, going back to this resonance structure here for sulfur trioxide, when we draw it this way, we don't put the lone pairs of electrons on the bonded atoms as we do in the other way. You can see that also in the example on page 275 at the very bottom there. It shows with dashed lines or dotted lines the shared or delocalized shared electrons. And again, no lone pairs on either of the oxygens. That concludes this lesson. Thank you very much for watching.